Right. The shear force acting on a beam at an I section with unequal flanges is 50 kilonewton. The section, as shown in figure, the moment of inertia of the section about neutral axis is 2.849 into 10 raised to 8 mm raised to 4. Calculate shear stress at the neutral axis and also draw the shear stress distribution over the depth of section. Right? So this is the cross section that is given. Now first let us try to find the center of gravity or the neutral axis of this particular section. So this is the section that is given. Uh, Let me draw a line here. And it is not exactly at the center. It is slightly above the midway of this web. So I'm calling this as the neutral axis. So this height from this surface here, uh, let me call this as y star. Okay, so this is y star. Y star is the location of neutral axis from the bottommost fiber, and I will name this as neutral axis. Okay, so this is my neutral axis. I need to first find this location. Now, how to find this location? We already have discussed this. Location of Na. Uh, y star is equal to I have three rectangles. Basically, it is a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. Right? Now, a1 is 130 by 50 and y1 is 25 mm. This is 50 millimeter and this is 50 millimeter. So I'm directly putting the values. I'm not writing the equation. So 130 into 50. This is my A1 into Y1 is 25 plus my second rectangle is this web, which is 50 by 200. So it is 50 by 200 into the center of gravity of this rectangle is at 200 by 2, that is 100 mm from this point, and this height is 50 mm. I'm finding y bar with respect to this. So 50 plus 100, so that is 150 plus the third rectangle is at the top, this one, this flange. This is 200 by 50. So 200 by 50 into now the center of gravity of this rectangle is from this surface at 25 mm, 50 by 2, right? It is here. So that is 25. This is 50, 50 plus this is 200 plus this is 25. 200, 250, 275 mm. 275. So This is A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3, right? So if you see, there is 50 common in all the rectangles, right? So I will write it like this: 50 into 130 plus 200 plus 200. Okay. So if I solve this, I will get the uh, y star. So let us solve this equation. This 130 into 50 into 25 plus 50 into 200 into 150 plus 200 into 50 into 275. So this is the numerator divided by 50 into 130 plus 200 plus 200. So this is 166.509, or I'll take it as 166.51. Okay. So I have found the location of y bar. Now let me go back to this diagram. Uh, Here, what I will do is I'm just naming or making few more dimensions here. Okay. So I'll call from the neutral axis to the top fiber. I'll call this as y1, and from the bottom fiber to the neutral axis I'll call it as y2. Okay. So I need to first find this y1 and y2, and then we'll proceed. So y1 is equal to, now what is y1? It is the total height of this I section, that is 300 minus y star. So y1 is equal to 300 minus y star, and that is equal to 300 minus 166.51. 300 minus 166.51 is 133.49. Okay. And y2 is equal to y star only. So I'll directly write it here. This is equal to y2. Right. Now, in the question, he says calculate the shear stress at the neutral axis and also draw the shear stress distribution over the depth of the section. Right. What does this mean? See, depth of section is this, right? Along the depth is this. This is the neutral axis. So you have to find the shear stress variation along this length, right? How the shear stress varies along this length, we have to calculate that, and then we have to draw the diagram. Now for that, I will first mark some salient points on this diagram so that it is easy for me to find the shear stress at those locations. So the top surface, I'll take this as A. Okay. The bottom surface of the upper flange here, this one I will take it as B. Okay. And this is the junction of the web and the flange, upper flange, right? I'll call this point as C. This is the neutral axis. Similar to these 3 points, we will have 3 points here, A, B, C. This will be D. This is the junction of the bottom flange and the web, right? And B, and this is E. This is the upper surface of the bottom flange, and this will be F, which is the bottommost surface of the bottom flange. So I have to find stress at 1, 2, 3, neutral axis 4, 5, 6, 7. These 7 points I have to find the shear stress, and after finding the shear stress I have to draw the shear stress distribution curve. Now let us find. I'll start from point A. So shear stress at oops, point A, right? Now, how to find the shear stress at point A? We have this formula. Where is it? No, I'll type it. Uh, tau, tau is the shear force, is equal to F by I into A y bar by B. Correct? So this is the formula we have derived earlier. Uh, I is about the neutral axis, which is given. F is the shear force. AY is the moment of area about the neutral axis at the section where you need the shear stress, and B is the width at that particular location. Now go back to this diagram. If you take this section, this is the topmost layer of the cross section. The area at this point is 0 because it is the topmost layer. There is no area available there for shearing. So since A, I'll copy this. Since AY bar is equal to 0 at A, so the shear stress will be equal to 0. Fine. So at point A, that is the topmost fiber, the shear stress will be 0. Now let's move to point B. Now shear stress at point B. Now what is shear stress at point B? B is the bottom surface of the flange, right? Now I am considering this rectangle, right? This is the cross section for a y bar. This will be my cross section. I need to find the area moment of this cross section about neutral axis, so that I will get the variation of shear stress between A and B. So uh, AY bar is equal to area moment, right? So area of this is 200 by 50. So 200 area is of this rectangle. So that is 200. Why is this down? Yes, 200 into 50 is my cross sectional area into y bar. Now y bar is the distance of the center of gravity of this particular section, this particular rectangle, with respect to the neutral axis, right? So this center of gravity of this rectangle is, this is 50 mm, 25 mm above this line BC is my center of gravity. So this is y1, y1 minus 25 or 50 by 2 will be y bar. So I'll put it as y1 is, I'll write it as this, y1 minus of 50 by 2, right? So this is equal to 200 into 50 into y1 is 166.51 minus 50 by 2 is 25. So 200 into 50 into 166.51 minus 25. So this is the area moment at that location, right? Don't try to write the unit for this because the unit you get theoretically is meter cube. This is
So,
not
sir,
volume. Yes.
Y1 is
sir, Y1 is 133.49, sir.
sir.
Yeah, yeah. Sorry, I took y2 value, right?
Yes, sir.
Yeah, 133.49. Oops. 200 133.49 minus 25 is this into 50 into 200, correct? So this is my AY bar for point B. Now I was saying, see, the area unit is meter square or millimeter square, and this is millimeter, so it becomes millimeter cube. Millimeter cube or meter cube is the unit for volume, and this is not volume, this is area moment. So better not write any unit, just write this value and leave it. Now at point B, the width of the section is 200 mm, right? So and B is equal to 200. So now put in this expression. What is F? F is 50 kilonewton, right? So it is 50 kilonewton, 50,000. I is 2.849, 2.849 into 10 raised to 8, right? AY bar is this value. I'll just copy this. This is AY bar, and B at this point is 200. So this is equal to, let me calculate this, 50,000 into area moment by 200 by 2.849 by 8. So the shear stress at this point is 0.952 megapascal. 0.952 MPa. Got this? Right? Now let us move to the next point, that is C. Right? This point. Now see, at point C everything remains same. Shear stress at point C, see at C the area above that particular section, right? At this section the area above this is this rectangle, but the width of the beam will be this thickness of the web, right? So that is the only change you have to make in this. So here a ay bar is this. I'll directly give the value of that. I'll not write everything. And B is equal to 50 mm. You got that? From here y is same, only this is changing. The width is changing. Rest all things remain same. Now put in this expression this value, you will get the stress. So here everything is same. This will become 50. That's it. Okay. So this I got by dividing by 200. So into 200 by 50. So this is 3.81. 3.81 megapascal is the shear stress at point C. Neutral axis, let us find in the end. Let me find DEF, right? So, say DEF you have to find in the same way we did for ABC. I'll start from F now. Now, shear stress at point F. Same logic as this. Since AY is 0, shear force, shear stress will be 0 at F, right? Bottommost fiber, there will be no shear stress. Then shear stress at point E, it is this point. Similar to B, we have to find for E. Now the area is this rectangle, bottom flange, and the distance we have to consider is this distance. Okay, so AY bar, I'll just copy this. It is, area is 130 by 50, and the distance of neutral axis from the center of gravity of this bottom flange. See, from the bottom surface at 50 by 2, we have the center of gravity of this rectangle, and this is y2, which is equal to y star. So y2 minus 25 will be y bar. So this is y2 minus 50 by 2. So into y2 is 166 something, right? What is that? 166.51 minus 25. Correct? Now let us calculate this. 130 into 50 into 166.51 minus 25. So this is some value. Just write it there. And B is how much? Can anybody tell? It is 130 there because I am taking this point E. When I come to D, A Y will be same, but B will be 50 there. Okay. Now let us substitute in this expression for shear stress. Tau is equal to shear force will remain same 50,000. I is same. A y bar is this value and B is 130. Okay, so let me calculate this. 50,000 into this by 130 by 2.849 by 10 raised to 8. So the shear stress at that point is 1.24, right? 1.24 MPa, megapascal. This is E, and now I will go back to D. Shear stress at point D. So it is same thing. AY bar is same. Just remove this. And here B is 50 millimeters, right? So just copy this same expression and change this by 50. So what you have to do this? This I got it by dividing by 130. So I'll multiply this by 130 and now divide by 50. So the shear stress at that point is 3.23. 3.23 megapascal. Okay, that is the shear stress at point D. Now the last section that is remaining is shear stress at neutral axis. NA, neutral axis. Now let me go back to the diagram. See, this is the neutral axis. Now y here will be 0, right? There is no distance. So AY bar will be this entire section. It is like a T section. This rectangle and this rectangle. So AY bar will be two rectangles. One is this flange, right? And this small rectangle. So let me do that. AY bar first I am taking the rectangle at the top, so it will be this only, 200 into 50, and directly put the values. Right, so it is 200 into 50 is the area, into 133.49 is y1 minus 25 is the center of gravity location from the neutral axis. Now I am considering this rectangle, right? This portion of the web. Now this height is y1 minus 50, right? Or I will put it like this and put this as y1 plus this height is y1 minus 50 into 50, right? So into 50. Now this is the area. Y1 minus 50 into 50 is area into y bar. Y bar will be half of this height, right? So it will be again into y1 minus 50 by 2, correct? So now let us substitute the values. Y1 is, where is Y1? 133.49, 133.49 and 133.49 and here also 133.49. Now let us calculate all this. Okay, I'll do this part first. 133.49 minus 50 is 83.49. This will also be same value, right? So I'll just square this into 50 divided by 2. So this is this part into 200 into 50 into 200 into 50 into 133.49 minus 25. I got a very huge value. Let me just check. I think there is something mistake in the calculation. Let me do it this way. 200 into 50 into 133.49 minus 25 plus this was 83.49 into 50 into 83.49 by 2. Ah, this is the correct answer. So this is equal to, just truncate this to one place, right? And B at neutral axis. What is the width at neutral axis? It is this width, which is 50 mm. B is equal to 50 mm. Okay. Now again use the same formula for shear stress. This will remain same. That will not change. Only changes B and AY. So AY is this and B is 50. Let's calculate this. 50,000 into AY by 50 by 2.849 by 8 10 raised to 8. So it is 4.419 or 4.42 megapascal. Now, if you use the dimensions as A, B, C, something like that, and you find the formulas for finding the shear stress for all this section, you will find that those equations for shear stress will be parabolic equations. So the shear stress distribution along this is parabolic. Now you have to draw the shear stress distribution curve. So what you have to do is you have to first project all these lines or all these points. So just projecting these now. Okay. Now I will use red color again and thicker line. This is my reference. Okay. So let me go to the top. At A and F, shear stress is 0, so no need to do anything. At B, it is 0.952, and at C it is 3.81. So I'll just, okay, from here to here, let us say this is 0.942. So I have made a parabolic curve. At this section BC, there is a sudden increase in the shear stress at the junction of web and the upper flange, right? So at C it is 3.18. So you will get a straight line there till this value. Okay, this is 3.18. Now at neutral axis it is 4.42. So let us say it is somewhere here. So it will be again parabolic. Here it is 3 point something. So you will get a parabolic curve like this. Okay. And at D it is 3.23, and above that it is 1 point something. So it will be like this. And sorry, it will be a straight line here. And then you will have a parabolic curve from here to, right? So this is the shear stress distribution for this given section. You have to just write the values. Now I don't have time for that. Whatever stress values you got, 0, this is 0.9 something, this is 3 point something, this is 4.42. Just you have to write these values and shade this region, right? So this is the solution for this numerical. Any doubts or questions?